So later on, after we finish all the applications, if the time is okay, then we can go back and then look at more examples, right? So the third one is called curve sketching, right? So this is a bit longer topic, okay? So let's quickly go through the outline, what's inside here, right? So first part is talking about extrema. Extrema is including maximum and minimum. Okay, together it's called extrema, right? Could be the highest, could be the lowest. So here we're just learning different terms, right? So we have different kinds of max, different kinds of minimum, right? So that's gonna take us several pages there, okay? And then second part is the Rolle's theorem and mean value theorem, right? So we'll go over that as well. And then number 3 is monotonic function and first derivative test. Okay, so monotonic, mono means one, right? So goes in one way, a function that goes in one way. And then we can use derivative to help us check, right? Testing for max and min, right? To make sure it's highest or minimum, right? And then number 4, we have second derivative test for concavity, right? So you have the first test and also second test, right? And then, so after we learn all the 4 things, we combine all together to make a curve sketch. So combining all the information that we have, we can graph a pretty well detailed function without using any calculator, right? So that's the use of one of the application of the calculus, right? It can tell you a lot of details that the graphing calculator cannot tell you, all right? And then that will be it, right? So hopefully we can cover half of it today, and then we'll save the other half for next time. So let's go back to curve sketching, part 1. So here you just need to know the terms. Maximum, we have the absolute max and absolute minimum, okay? So let's go through the definition, right? So here I give you a function. It has to be continuous, right? So please underline that. On the closed interval, so this is the key, must be closed. When we talk about absolute maximum, it has to be closed interval. What's the difference between closed and open interval? Jeffy? Do you know?
Is it like if it includes the 2 points?
Yeah, which one includes 2 points?
Like the square brackets are the ones that include the 2 points?
Yes, very good. Okay, so closed interval means we include the points at the ends, right? So we have A here, B here. So this symbol represents what we have up there, right? A shorter way, faster way to write it, right? So if it's continuous in that interval, and also there exists a number C such that the Y value at C is higher, right? Greater or equal, right? Higher or equal to the function for every X. Then that place is called the absolute maximum value, right? F of C is the maximum value. So we're talking about the Y, right? So one example will be like, if I draw a graph, let's say like that, then we would have an absolute max will be at, so here's A, here is B. So this is closed interval, right? You can tell it's closed interval because the end is a solid dot, right? Not open circle. So we are looking for a place C such that if I go up, right, and find the Y value, so that will be F of C. that value is the highest point of the whole picture, then we call that absolute maximum. Okay, so you compare with the whole function within that domain, right? So of course the absolute minimum will be the opposite, right? So same thing, closed interval has to be continuous as well, but this time the function, the y value has to be less than, right? Then it's called absolute minimum, right? Before was maximum, right? So for example, like the first graph we have here, let's label this one. This one is absolute maximum. So where is the absolute minimum for this graph? Joan?
A.
Yeah, it will be A, right? So f of A will be the absolute minimum value, right? Okay, and then so it could happen at the endpoints, right? So you can write it at the bottom or in the middle, okay? So absolute extrema could be at endpoint. Okay, and then another example, let's draw another one. Let's say if it's going like this. So we have endpoints here, right? So where is the absolute max? Emily?
At A.
Yeah, at A. Okay, very good. So this one, f of A is absolute max. Okay, and Leon, where is the absolute minimum? Can you draw it out?
Oh, yeah. Around here?
Yeah, very good. Okay, so you just find the lowest point for the whole graph. Okay, pretty easy. Okay, so we have this place. So when they ask you what is the absolute max, absolute min, it's looking for the y value, right? So this one will be f of c. This one is absolute min. So if you get 2 points, that's the same height, right? Let's say, yeah, if B and A, they are the same height, right? They are both the highest, but you still have the only one absolute value maximum, right? But then it could happen at 2 x's. Right, so here we have an example here, okay, question 9. So given a function f of x equal 3 over x continuous, right? So that's a keyword, right? It has to be continuous on this interval. So you see this bracket is a bit different. We have a closed, right? This is a closed. And then the other side is open. Okay, so please sketch the graph and then determine any extreme value. Extreme value includes max and min. Okay, so make a sketch. You don't need to draw too many points, right? You can plug in points, right?
Jason?
Yeah.
It says it needs to be on a closed interval, but this one has open on 3.
Yeah, so it has open, so there it cannot happen at 3 then, right?
So it has to be anything that's not 3.
Yeah.
Okay.
Okay, so you just look within there, right? Is there any place that has a extreme point? Okay, so if you finish the graph and also have the max and min value. So for max and min value, please write it out like f of something equals something, right? So this way I know both the x and y value for the extremas. You can get the graph by plotting table of value. If you
Jason,
don't know what it looks like. Yeah.
wouldn't absolute minimum be right before 3 then?
Absolute minimum right before 3. So is there a point?
Wait, like I don't know, like it's like 2.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 Okay. Yeah.
What do you think?
Do I put like 3 minus like at the top?
Okay, you leave it open for now. Okay, let the other people.
Okay.
Okay, if you got a graph and write down what you think about max and min values, please raise your hand. All right, so here, let me just quickly draw the graph, right? At plugging 1, it will be 3, right? Plugging 2 will be 1.5. Plugging 3 will be 1, but because it's open, so I have to draw an open circle. Right, so clearly, right, the absolute max, we have it at 1, right? F of 1 equals to 3. Okay, and then absolute min, just like Jesse said, I could go down, right? But because it's open, I can get as close to 1 as possible, right? The value for minimum, but you can never reach it, right? So for this case, there is no absolute min. Okay, so if it's an open interval, right? In this case, right, in the lowest place looks like it's at the open circle part, then you cannot find a single value and you call that the absolute minimum. So this one, you just say none. Okay, so I picked this example so you know sometimes you could have, and also why it doesn't have an absolute min. Okay, so we could also have piecewise. So same thing, please draw this out. 2 pieces. Find all the extreme value on the closed interval 0 to 2. Okay. So same thing, if you finished, please raise your hand. Anyone here doesn't know how to graph the piecewise?
Jason,
Yep,
can you have 2 max?
you could, but then the value value can only be 1. It could happen at more than 1 place,
Okay.
but the y value can only be 1. Okay, let's check if you have the same graph as mine. So to graph piecewise, you take the endpoints, right, and plug it in. So 0 goes in will be 1. 1 goes in will be 2, but that one is an open, right? So you got to keep it open. And we know it's a parabola, right? Opens up, so just make it look like a parabola. Second piece, if we plug in 1, it will be 0. Plug in 2 will be 1. And we know this one is a straight line, right? And they both have closed. Okay, so if you have the extreme values, please raise your hand. Okay, Nicole, what's the absolute max?
Is the absolute max 2?
At x equal 2, or I need to know f of what equals to what?
F of 1. Wait.
Yeah.
I'm a bit confused.
A bit confused. It's kind of, it's different from limit, right? If we're talking about limit, right, approaching 1, then the limit will be 2. But we're not talking about limits. We want to find exactly where the highest point, maximum means highest point is. How about you, Joan? What do you think? Where is the absolute max?
I kind of put none, but I don't really know.
Why do you think it's none?
Because the last question, because it has to be a closed interval, but I don't really know.
Okay, so we want to find the highest point of the whole graph, right? So the highest, we do have a highest empty circle, right? But then that's not a point. The highest I could get, right? I can only get here, right? Or even higher, right? I can zoom in more. Oops, the graph disappeared. I zoom in too much. Okay, where did it go? Okay. Right, so I can zoom in a lot, try to get higher, right? So I could have a point here, I could have point there, but you can never tell a single point and then you call that the highest point. So yes, you are right. Okay, so this one is none. How about absolute min? Leon, do we have any absolute min?
F of 1.
Equals?
0.
Yeah, make sure you write both values, right? So it shows the x and also the y point, y values. If they are asking what's the value, then you only answer the y, right? Okay, next part. So these two are similar, okay? So we're gonna skip these two. We'll look at next term. So another kind of extrema is called the local max, local min. So let's look at the definition here, right? If there exists a number c in small, right? This is important, small and open, a to b, right? So it'll be a less than x less than b, right? There's no equal signs, such that f of c is greater, right? Means higher for all the x in the open interval. So because we're only talking about open interval, so it cannot happen at the endpoints, right? So you can make a note as well. So for local, right? This is also called the relative, right? Local or relative extrema never can't spell today. Keep writing it wrong. Never at endpoint. Okay, so that's the biggest difference between local and absolute. Absolute max and min can happen at endpoints, but local can't. Okay, because it has to exist within a small interval. All right. So for example, local min will be opposite, right? So let's circle those keywords: small and open, right? Less than means lower, right? Then it's called relative or local. So let's look at the previous graph. For example, like this, the top one here. Right, so I want to be able to find a small interval, right? Doesn't matter how small it is, but within there, I can find either the highest or lowest. So for example, the first graph, I'm gonna use green, okay? So I could say the interval is here to here, right? Because if I go up from here and then to here, I have a lowest point, right? So this will be called the local minimum, okay? Because within that small interval, I am able to find a point that is the lowest, right? Do we have any local max in this graph? Anyone? Do we have any local max?
No.
No local max. There's no other interval that I can make.
Oh, yes.
Highest point.
Yes.
Where?
Yes.
Can you draw it?
In between the well, basically wherever you want, right?
You show me where is the interval.
Do you want me to draw it?
Yeah, please draw it out.
Okay.
Yeah, okay. So basically you just cut a section, right? Small interval is like a section of the graph. And then within that little section, you're able to find a highest point and just call that local, right? So as you can see here, right? Absolute max can also be local, right? Local max, right? But then if it's at, so because it needs a small section, right? It cannot happen at the endpoint, right? If I try to make an endpoint here, there's no left end. The graph ends at A, right? So that's why it cannot happen at the endpoint. Okay, so let me clear the drawing first. Okay, so let's go back to there, to the previous page. And then we can write another point, another important point here. Local, relative, extrema could also be, right, could be absolute extrema too. Okay, so two important things to remember, right, between the local and absolute. So at the bottom, please identify all the extrema, right? So we have four kinds: absolute max, absolute min, local max, local min. Okay, you just list out the letters And when you finish, just raise your hand.
Wait, sir.
Yeah,
For local,
yeah.
it could be the same as the absolute, right?
Yeah, it could be the same.
Okay.
So you need to remember the definition, right? How we find them. Then you know where, like whether it's a local or absolute. So for these questions here, these two examples, you don't need to write f of something, okay? You could just list out the letter, okay? It's faster. Please raise your hand if you finish both.
Jason, can I go to the washroom really quick?
Yep, of course. Okay, let's check a few answers first. Okay, Leon, what's the absolute max for first graph?
B.
Okay, absolute min, Jeffy, absolute min.
How about a C?
Yeah. Local max, Carrie,
B.
B, B or D?
B.
B. Any more?
Would D count too?
Okay, well, as long as you can make a small interval, right? So for example,
Oh, okay.
right, make a small interval, and then within that, right, you only focus on locally, right? It's like you look around your neighborhood, right? So you have a highest point. So D also count. Any more?
I think that's it.
That's it. Okay. Lex, how about local min?
For local men, I wrote
I can't hear you.
for local men,
Yeah.
I wrote C or E. C and
C
E.
or E. Okay. Yeah. Any question about question A?
Wait, so we can have 2 for local?
Yeah, you could, right? And remember, you follow the definition, right? So think about you are looking for the highest place on Earth. Then that will
Yeah.
be called the absolute, right? So
Mhm.
you find the highest elevation. But then locally,
Oh,
right, we could have Whistler, right? Whistler is pretty high, right? Locally in
yeah,
BC, right? But then
yeah.
Rocky Mountain maybe even higher, right?
Okay, yeah, I see.
Yeah. So local and absolute very different.
Okay.
Okay, let's move on to B. Let's check. Emily, do you have absolute max?
Yeah, I have E.
E, okay. And Nicole, absolute min?
I have F.
F, okay. Local max, Leon?
E and C.
E and C. And Joan, local min? Are you back? Okay, she's probably not back yet. Okay, Jeffy?
Can I ask
local
something?
min?
Can I ask something?
Yeah,
Is F, is that a point or an arrow?
point, that's a point.
Oh, okay, because I thought it was like continuing on.
Yeah, okay, that's a
Oh.
point. Yeah, single point. So it stops there. Yeah, local min. Do you have that, Jeffy?
Is it B and D?
B and D. Yeah, B and D. Okay, so I think everybody clear about local and absolute, right? The difference. All right, so now you know the terms. So later on, you could have question. They say, please find, right? They will give you a function and want you to use derivative to help us find absolute max, local min, right? Whatever. Okay, now before we get to there, right? There are two theorems that we need to go over. So it's on next page. The first theorem is called the extreme value theorem. So this one basically what it's saying that there is, how do you check if there is an extreme value, right? Extreme value includes all the four things that you learned just now, right? So it says if f is continuous, right? So that's always important, right? And it's closed, right? Continuous on closed interval, then there has to exist a value C and D such that it's an absolute max and absolute min. So it's saying that it guarantees for you to find absolute max and min, okay? So if it's continuous in that closed interval. So no matter what kind of function it is, right? So that's what this theorem is saying. So for example here, right, this is closed interval, right? And then I could have a closed interval here if I want, right? I could have A here, B here, close here, close there. No matter what kind of graph you draw, right? I can say A here and then B here. You always guarantee to get absolute, right? If you cut the graph off, okay, within that interval. Right? So let's put in simple words, right? So F continuous on A, B means guaranteed to have absolute extrema. Okay, in textbooks, sometimes they put in a more formal way, right? But if we put it in plain words, easier to understand. Okay, next one is called the Fermat theorem. Fermat theorem is talking about local. Okay, so here is saying that they tell you that f of c is a local extrema. Okay, so when you see the word local, you have to remember it's an open interval, right? Locally. Defined on here, right? So you see here, this is open, right? Open interval. And then C is an element of A to B, right? This symbol means an element, right? Part of it, right? An element. of A to B, right? Could be any point within A to B. If that's the case, right, if you know it's local, then the prime there has to be 0. So that's the first condition, right? But only if the derivative exists. Okay, does anybody remember which places the derivative does not exist? Derivative means differentiable, right? So which places it's not differentiable? Anybody remembers? Where on the graph it could be not differentiable?
Endpoint, and then if there's not endpoint. What's the thing called? Like
Endpoints, what else?
the corner thingy.
Corner thing, yeah, yeah.
And then
Yeah,
there's like
four places.
asymptote thing.
Asymptotes.
Yeah.
One more.
And then if it's like a jump.
Jump, sure, yeah, okay. So endpoint, cusp, or corner, right? And then we have the jump, yeah. And vertical. Vertical tangent, right? Vertical slope. Those are not differentiable, right? So f prime not exist at, right? This is saying not exist. So this is just a review, right? So it has to exist first, and it equal to 0, right? Then, okay, so this is the conclusion, right? If it's local, then we know the slope has to be 0. And then, or it does not exist, right? It could be two possibility. So does not exist, you can look at the top, right? We just reviewed that. It could be those 4 places. Okay, so let me repeat again. If you know it's local, then the slope either equal to 0 or doesn't exist. Okay, so here I give you a couple examples here. Do we have any local? Can you help me circle it? Where is the local? Local extrema. Anyone wants to try? Joan, are you back? Oh, who's doing it?
Yes, hi.
Hi. Okay, who's the pink one?
Oh, that's me. I
Oh,
started
yours?
drawing.
Okay, okay, that's cool. Yeah. Okay, so yeah, so those are the local min, local max. Yeah. Okay. All right. Very good. So these are the points C, right? C and C will be here. There is another C there. Okay. So Jesse, can you help me clear the drawing?
Oh yeah, my bad.
Thank you. No, it's okay. Okay. So we found the 3 location, right? 3 local ones. So it's saying that if it's local, then the slope has to be 0. So let's see if that's true, right? I draw a tangent line there, right? It's 0. Draw a tangent line there. That's also 0. That's also 0, right? So that's what the Fermat theorem is saying. If it's local, it must be 0. Okay. The second part is saying that if it's local, the slope could also be not exist, right? So over here, is there any local max or min? Joan, do we have local max and min here?
Do you want me to draw or just
Yes,
say?
please. Yeah, you can draw it out.
Okay.
Wait, Jason, was I supposed to raise my hand for something?
No, you don't need to raise your hand.
Oh, okay. I just thought everyone else's hand was raised and I got concerned.
Okay, I forgot to lower their hands. Yeah, Joan, did you draw it yet?
Sorry, I'm thinking. Cause
Okay.
for
local max or min. Do you see any local max or min?
Yeah, wait. I'm
Okay.
trying to do this annotate thing.
Yep.
I think this could be one.
Okay, so yeah, very good. That's the one. Okay, that will be the local what?
Min.
Local min. Do we have local max?
I don't think so.
Very good. Okay, can you help me erase, please?
Sure.
Yes,
I
Jesse?
thought we just said it doesn't exist. Like if it's on a corner though.
Yeah, so first, right, you have to watch out the order, right? It says if it's local, right? So we have a local min here. This is a local min. Then it could be not existing, right? This, what would you call it? This place. Which,
Oh wait, it
we-
exists because
Yeah.
the local thing exists because because it can't be differentiated. Is that what it means?
no, you have to start with if it's local first. You have to make sure it's local, right? Then you check the slope there,
Oh,
right? If means happen first, right? And then we look at the slope. First, you make sure it's local, and then you check the slope, right? Then means afterwards. So that's why I asked Joan to point out the local, right? So she says, okay, we got a local min. Now let's look at the slope there. Do we have a slope there at that point? What's the prime at that place? Emily?
Doesn't exist.
Yeah, this one doesn't exist because it's what, Emily?
It's a cusp
Yeah, because
or
of
corner.
or corner. Yeah, okay, we will call it a cusp. So that's what definition Fermat theorem is saying. Okay, so you have to start with checking it's local or not, right? So it's like I'm saying if outside is sunny, right? If outside is sunny right now, right, very hot, then the roadway must be dry, right? So right now, if you look outside, right now the road is very dry. Okay, so that's why it's saying you have to make sure it's sunny first, and then the second sentence can carry out to be true. Now, the second part, there's a note here, right? So please make a circle. It says the converse is not always true.
wait, sir, I have a question.
Yeah, Jesse.
Wait, so I don't understand. Is there a local minimum or no?
Yeah, there's local. We already confirmed that first, right? You have to make sure it's local first. And that
Wait, so then
yeah.
no. You can go ahead.
Okay. If we confirm it's a local minimum, then the slope there, it could either be 0 or it could be doesn't exist.
Oh, okay. I understand.
Okay.
Thank you.
So the first thing to do is to get as local first, right? To confirm that. However, right, the converse of the Fermat is not always true. Converse means if we swap the order around, right? For example, I said if it's sunny, then the road is dry. Now reverse, right? If the road is dry, then it's sunny. Is that always true?
No.
When would it happen then? When would it be not true? If the road is dry?
Because it rained yesterday, and there's like a little hole in the thing, or like it like dips down, so there's still like water on the road.
No. Converse means you have to say if road is dry. I already know the road is dry. Then it's sunny. Should I write it out so you know what I'm saying?
Yes,
It could
please.
be cloudy instead.
There you go. Okay, Joan got it.
Oh.
If sunny, then road is dry. I think this example is not really good, right? Because sometimes this one is not always true. Let's think of an example that's always true. If If what? If it's raining then, okay? If it's raining, then what? What could happen? If it's raining,
Then the road is wet.
the road is wet. For sure, right?
Yeah, guaranteed.
It is wet. Converse will be the road if, okay, I have to start with if. Road is wet, then it must be raining. It's raining. So is it always true?
Nope.
Yeah, so this one, the first one is always true. Right? This one is not always true. Okay, so that's what converse means. So right now it's saying that the converse of the Fermat is not always true. So let's write down what it sounds like then, right? The converse of Fermat. So if the slope is 0 or the slope is not exist, then it's local. Okay, I think I better write the point as well. If the slope at point C is 0, if the slope at point C is undefined, right? If either that happens, then it's a local extrema. At f of C. So it's saying that this is sometimes true, sometimes false, right? So now we have to reverse. I check the slope is 0, right? Oh, the red line. So this one will be true, right? Slope is 0. You can see it's local extrema. Same with this one, right? We have cusp, right? You start with checking, okay, I found a place that has no slope. Then that place is also a low. You see the order I say it, right? I check for slope first. Now for this one, do we have any cusp or slope equal to 0?
At 0, 0.
Yes, okay. If we draw the tangent line, right? So for example, here's a tangent, right? Tangent. And then at the middle part, this place has prime of 0 equal to 0, right? At this origin, right? Would you call that place a local max or min?
No.
Right, okay, because this is right in the middle, right? If we make a small interval, it's continuous getting higher, right? So it's not really like a hill, right? Or a valley, okay? It has to be either a hill or valley to be a local max or min. So that's why the converse is not always true, okay? So not always true. However, it gives us like sometimes true, right? So at least we can get the possible candidate, right? Possible location for the local max and min. Okay, we could still use it, right? We could still check for prime equal to 0, prime equal to undefined. Then at least we limit down, right, to a few choices, right? At least we have a direction. Okay, so that's what we are going to do, right? We want to find out where the slope equal to 0 or undefined, and then make sure they are local max or min. Okay, so those places we have a name. It's called the critical values. Okay, so that leads us to page 90. Okay, continue from Fermat theorem. So if the value C satisfies one of the following three conditions, right? You just need to meet one of them. Then C is called a critical value. Okay, critical means very important. Important means because they could be, right? Let's write it down. Could be extrema, right? But not guaranteed though, right? We already just went over that, right? Could be extrema. So first condition is equal to 0, right? Second condition is does not exist, right? Third condition is at the end, which is also part of doesn't exist, right? The slope cannot happen at the end. So at the end of the domain. All right, so here we're just gonna practice how to find critical values for a couple questions. Let's do, I think polynomial is too easy, okay? Let's do question B, 12B, okay? We'll find critical values for this one. So let's look at question B. All you need to do is prime it first, okay? And then make it equal to 0 or undefined, okay? I'll let you prime it first. Okay, so please raise your hand if you finish the derivative. Anyone has question? Right, I've been talking too much today, right? Because it's all about theorems. Any part of the theorem that you're not clear, let me know. Have you finished the derivative? Shouldn't take that long. Any question? Leon, Joan, Nicole? Yeah, got it? Emily, do you have the prime?
Yeah, I do, sorry.
Okay, what's your answer?
Oh, I have 4/3 x to the power of a third plus 4/3 x to the power of -2/3.
Okay. Right, and then we can simplify this, right? Because right now we want to find out the places that makes it equal to 0 or undefined, right? So instead of making it equal to 0 first, I want to simplify first, okay? To simplify this, we need to factor it, okay? So we'll take out the 4/3. Okay, factor GCF, and also I'm going to take out the x to the -2/3, right? Because I don't like having a negative exponent inside. So this GCF, please write down what's left, okay? And also raise your hand if you finish factoring. All right, this part is the GCF. When you factor GCF means you divide it by what you factored out, okay? And then after that, you put it into a single fraction. Anyone has trouble getting the thing inside brackets? Leon, do you know how to get things inside?
Oh, I just forgot to raise my.
Okay, so what's your answer, Leon?
Inside the bracket, I have x to the negative half plus 1.
Okay, how do you know it's x to the negative half?
Because when you factor out x negative 2/3, you're like dividing it, and when you're dividing the exponent, you're like, oh, you're subtracting it.
Yes. Which
Oh,
one?
whoops, I made a mistake.
Which number subtract which number?
1/3 minus 2/3.
Minus negative 2/3. Okay, you have to subtract the exponent that you take out. So let me know what you got.
Just x.
Just x, right? So x to the 1. And then we can put them into fractions, right? 4 will stay on top. X plus 1 stays on top, right? 3 is at the bottom. X has a negative exponent, so it goes down, right? So cube root x squared. Any questions so far? Anyone? So once you get here, we are looking for places that makes the slope either equal to 0 or undefined, right? To make it become 0, then you look at the numerator, right? Whenever numerator is 0, the fraction will be 0, right? So prime will be 0. You look at the top, and to make it undefined, right, you look at the denominator, okay? So by looking at those two places, we know our critical value. So what x value makes it equal to 0 then? Carrie?
0 for the bottom.
For the top, how do you make the
Oh,
top?
for the top is -1.
Yeah, okay. And then how about the denominator?
0.
Yeah, okay. So when x equal to -1, then the prime is 0. When x equal to 0, then the prime will be undefined, right? They are both called critical values because they are the possible place, right? Possible location, right? Possible local extrema. They're only possible, okay? Maybe it's not, right? So we have to confirm later. We'll learn how to confirm that, okay? So that's how you get critical values. The first critical value came from prime equal to 0. The second critical value came from prime is undefined. Anyone has questions here? Any steps unclear? All right, so we are gonna do similar things, okay, for another question here, right? Question C. Okay, so same thing, please find the critical values, this time by yourself. So all the rules that you learned before, okay? Power rule, quotient rule, product rule, implicit, right? Chain rule, okay? Trig, right? All those things, you apply it whenever needed. So at the end, you just list out the critical values. So once you got them all, please raise your hand. You need to double check your prime, okay? So I'm just gonna write it on the side. Okay, Emily, have you finished the derivative?
I'm just simplifying it.
Okay. JC, what's your simplified derivative?
Okay, I don't know if I did it right, but okay, here goes. I got 1/3 x to the power of -2/3 times x minus 7 squared, and then plus 2 x to the 1/3.
I want the simplified version. Did you simplify?
What does that
it?
mean?
Like factored.
Oh, okay. Oh shoot, I think I did the factoring wrong. I just realized I made a mistake.
not the
Wait,
first
I'll redo it.
Okay, okay, not
Sorry.
just not the first step. Jeffy, how about you? Have you finished simplifying?
I'm still simplifying it, but I have the unsimplified version.
Oh, okay, okay. I want the simplified one. How about this? If you guys already finished simplifying, please raise your hand.
I think I got it.
Okay, yeah. Yeah, what is it?
Oh, you okay. I got x to the -2/3 and then bracket x minus 7 x minus 1 all over 3.
Okay. All right. Anyone else?
Except I'm like 99% positive it's wrong.
Oh, okay. Okay. Yeah, we'll see. It's okay. Anyone else? Jeffy, do you have the same form?
No, but Jesse's looks a lot more concise than mine, and I'm really worried. But I have it factored as x to the 1/3, and then open bracket, and then big fraction.
Inside?
So like, yeah. So in the numerator, it's x to 2/3
Okay.
times, or I guess bracket x minus 7 squared.
Yeah.
And then in the denominator is just 3. Oh, it's not that big, but okay. And then plus 2x minus 14.
And then close bracket or
No. It's still in the bracket. Plus 2x minus 14.
plus 2x minus 14.
Not in the denominator.
Huh?
Not in the denominator.
Oh, okay. Okay, I see. That's quite long, eh? Plus 2
that's fine.
minus 14.
Yeah.
Yeah? Okay. Lex, do you have the simplified derivative?
Okay. So this is the whole fraction. So on top.
You gotta speak closer, please.
Okay, so this is one fraction. So on top it's x bracket x minus 7. And then another bracket x minus 7.
Can't hear you.
Well, basically just 2x minus 7, I guess.
Huh?
2x minus 7. Close bracket. Yeah, and then underneath it's
Huh?
3. On the bottom,
Uh-huh.
it's 3 cube root
Huh?
Cube root.
2 root
Cube. Cube.
a cube. Sorry. Okay. Can you say one more time?
Cube root.
Cube root. Okay.
X squared.
X squared.
Yeah, that's it.
That's it. Okay. Well, so yours pretty close to Jesse then, right? Yeah, because for Jesse, we could also move his top to the bottom, right? Then you get a cube root and x squared. So you have one bracket that's different. Okay, how about the rest of you, huh? Joan, Carrie, Leon, how are you guys doing? Are you done simplifying?
I got the same as Jesse.
Same as Jesse, okay?
I'm kind of having a bit of trouble simplifying, but mine is like looks similar, or it's getting similar to either Jesse's or
How
Lex.
about you tell me your first step, Joan? What's your first step?
So I'll just say it's really long though. So bracket 1/3x to the power of -2/3,
Mm-hmm.
and then times by bracket x minus 7, all that squared,
Mm-hmm.
plus x to the power of 1/3,
Mm-hmm.
and then bracket 2, and then times x minus 7.
Mm-hmm.
And that would be times 1, but I just didn't include it because.
Okay, very good. So this one you applied which rule?
Product rule and also chain rule.
Yes, product rule and also chain rule. Very good. So next step you will be factoring, right?
Yes, and I was having trouble factoring.
So can you tell me what you factored out then?
I don't know.
Well, usually we take out the things that looks ugly, right? Looks complicated.
Yeah.
Right. So let's start with the one section at a time, right? We have 1/3, right? The coefficient ones, the 1/3 and the 2, right? Those are coefficients.
Mm-hmm.
Which one you don't like it? Which one you don't like more?
1/3.
1/3. So you take out 1/3. That's how you choose.
Right.
Okay. And then we also have x to the -2/3, x to the 1/3. Which one you don't like more?
X power of -2/3.
Yeah, so we take that out. Okay.
Yeah.
Is that the same choice as yours?
Yeah, that was like kind of the idea I was going for. I think I just got my math messed up though.
Okay. Anything else you can also take out?
I mean, both have x minus 7.
Yeah, and what's the most we can take out?
Just 1.
Yeah, to the 1. Okay, so this whole thing here, this is the GCF. Okay, and then let's write down what's left then. What do you have the leftover?
X minus 7
Yeah, x minus 7.
plus x. Oh, and 2x.
2x.
Yeah.
Times the 2, right? So 2x. And then, of course, we can simplify this, right? Any mistakes so far, anyone? Or any questions? How we get the leftover? Okay, so let's simplify this. 2x plus x minus 7. So that will give you what? Well, hold on, it's not 2x. Wait. Not 2x. Should be what? Instead of 2, what should it be? Because remember, if you take it out, you need to divide by 1/3.
Oh, yeah.
Yeah.
Okay, I thought something was weird. Okay, that's where I got my math messed up. It'd be 6.
Yes, it will be 6, right? You can double check by multiplying back in, right? 1/3 times 6 will give you back the 2, right? So that way you know it's correct now. Now we can simplify more, right? The green part, that will be 7x, right? 6x plus an x, so 7x. So we can sort of write out the fraction now. We have x minus 7 on the top, 7x minus 7 on the top as well, right? 3, and then the cube root x squared. So let's see, do we have any match here?
Oh wait, yeah, no, I forgot the 7.
Yeah,
I was waiting for you to finish with Joe. I wanted to put a 7 by my thing.
okay.
Yeah.
Yeah, so we need a 7, right? 7, yeah, of course you can factor the 7 out, but I think it's fine here. Right, so to get the critical values, right, so by looking at the final result, so you see it's very important to do derivative 100% all the time, right? Otherwise, everything comes after, right? All depends on it. Okay, so please get the critical values and then raise your hand after I lower your hands. Okay. Please raise your hand if you got all the critical values. Right, Leon, what's your critical value?
I got 710.
Yep, 710. Okay, 7 1 came from the top, right? When prime equal to 0. 0 came from the bottom when it makes the prime is undefined. So those are the possible place for local extrema. Okay, so these 3 places. So let's have a break first. After the break, we'll be starting to do some graphing. Okay, so I'll see you in 15 minutes at 6:30.
Thank you.
Okay, you're
Thanks,
welcome.
Jason.
Yep.
Yeah.
Bye.